The Borsuk-Ulam theorem is one of my favorite theorems in all of mathematics. And for me, it represents what is best about math. It has a really simple, clean statement. And at the same time, in order to prove the statement, you need to come up with some really clever and deep insights. The theorem has many interesting proofs using ideas from different parts of mathematics, which is for me also a sign that something really fundamental and basic is going on. In this video, I'm going to present the proof that I like the best. This proof uses the concept of simplicial complexes, and I think it's a great way to learn the basics of the concept of simplicial complexes. So let's start by just stating the theorem. Let's define Sn to be the n-dimensional sphere. So that's this set. It's a set of points in n+1 dimensional space whose length is exactly 1. The theorem says that if f is any continuous map from the sphere to n-dimensional space, then there have to be two antipodal points on the sphere, so a point x and minus x, that get mapped to exactly the same point in n-dimensional space. Okay, so it's a very simple statement, but the statement is very interesting. For example, what it says is that if you have a rubber ball, and you take this rubber ball and twist it, stretch it, fold it, do any kind of manipulation of that type, and then flatten it onto the ground, then no matter what you do, there will always be 2 points that were antipodal on the ball initially that now lie on top of each other. Okay. Another way to think about the theorem is that at any point in time, there are 2 points on the Earth that are antipodal, so they're exactly opposite of each other, and yet they have exactly the same temperature and humidity. Let's say. Okay, so if you take any continuous map from the sphere to n-dimensional space, then there will be 2 points that are antipodal and get the same value. Now, it's not too difficult to prove the theorem when n equals 1. Here's a picture of the one-dimensional sphere, and let's say you have some map that takes the points on the sphere to the real line. Then just take any 2 antipodal points, okay, x and minus x, and in general, the values of f of x and f of minus x will not be the same. But now just start to walk around this one-dimensional sphere until you've swapped the locations between x and minus x. And you see at some point, the values of f of x and f of minus x must be equal, right? Because they have to exchange locations. So at that point, you will have found an x and a minus x that have the same value. That proves the theorem for n equals 1. Now, it turns out the theorem has many equivalent forms that are also very nice. And here's one example of such a form. So let's say you can cover the n-dimensional sphere with sets a1 through an+1, with n+1 sets, where every ai is either an open set or a closed set. Then there will be a pair of antipodal elements, x and minus x, that both belong to the same set. Let me explain how to prove theorem 2 from theorem 1. Suppose you're given n+1 sets a1 through an+1, as in theorem 2. Then you can define a function f of x mapping the sphere to n-dimensional space by taking the first n sets and defining the ith coordinate of f of x to be the distance of x from ai. Okay, so this is a continuous map. And by theorem 1, there must be 2 antipodal points that get the same value under f. And intuitively, if the value here has a 0 in it, then x must belong to the corresponding set. And if all of the values, if f of x has no 0 coordinate, then x must belong to an+1. Okay. Now that's not quite a proof, because it's possible to have 0 distance from a set and still not belong to the set, if that set is open. Okay. So this is not exactly a full proof, but it can be turned into a full proof, and I'll leave out the details here. One of the nice things about the Borsuk-Ulam theorem is that it has many surprising applications, including to combinatorial problems. For example, you can use the theorem to prove an optimal lower bound on the chromatic number of Kneser graphs. So let me explain that connection. Suppose you have the universe 1 through n, and you want to associate to every subset of this universe of size k a color. You want to associate a color from one of our colors in such a way that disjoint sets get distinct colors. So your goal is to try to color the subsets of size k so that disjoint sets get distinct colors. Okay. So the question is, how many colors do you need to do this? Well, here's the first idea for finding a coloring. Assign to each set the minimum of the set as the color. And this will give you n minus k plus 1 total colors. Because the sets are of size k, the minimum cannot be larger than n minus k plus 1. So here's a more efficient coloring. Let's color every set T with the minimum element of the set and the number n minus 2k plus 2. So this coloring uses only n minus 2k plus 2 colors, and I claim that it's still a good coloring. And the reason is, if you have two disjoint sets A and B, if one of them gets colored by its minimum, then the coloring is still valid for the same reason as before. On the other hand, if both of them get the color n minus 2k plus 2, that's not possible, because that means that A and B are two disjoint sets that are both contained in the interval n minus 2k plus 2 up to n. And that interval is not big enough to contain two disjoint sets of size k. Okay, so this is another valid coloring. And the beautiful theorem is that this coloring is actually optimal. Okay, you can't do better than this coloring. Every coloring requires exactly n minus 2k plus 2. It requires it. Every coloring requires at least n minus 2k plus 2 colors. Okay, so let me now show you how to prove this theorem using the Borsuk-Ulam theorem. So suppose, for the sake of contradiction, that we found some coloring with fewer colors. Now here's what we'll do. Let's consider the r-dimensional sphere and take n points in that sphere and choose the n points in such a way so that no r plus 1 points lie on an equator. Okay. So place n points on the sphere in such a way that no r plus 1 points lie on an equator. If you just place the points randomly on the sphere, then with high probability they will satisfy this condition. Okay. And now for every x on the sphere, define hx. This is the hemisphere where x is the North Pole. Okay, so in this picture, if x is up here, then h of x consists of all the points that are above the equator corresponding to x. So it's the set of points y in the sphere that have positive inner product with x. And now I will define a collection of sets A1, A2, A3, and so on, where the set AI will contain exactly those x which have the feature that there's some subset T of points that lie inside h of x and are colored with the ith color. Okay, so this gives R sets, each one corresponding to one of the color classes, and x is included in AI exactly when there's a set T in h of x that gets colored I. And finally, you define AR plus 1 to be all remaining points, all the points of the sphere that were not covered by one of the AIs from before. Now you see that A1 through AR are open sets, and AR plus 1 is a closed set. So we can apply the theorem from before, which says there must be two antipodal points, x and minus x, that belong to some ai. Okay. Now there are two cases. If I is at most r, if x and minus x belong to one of the ai's that corresponds to a color, then the coloring is not valid, because it must mean that there's a subset T in this part of the picture and a subset T prime in this part of the picture that are disjoint yet get the same color. So that's not possible. That contradicts the fact that the coloring is a good coloring. If I is equal to r plus 1, that means that there is no k-tuple in hx and no k-tuple in h of minus x. But then there must be at least n minus 2k plus 2 points lying on the equator. And that's r plus 1 points that lie on the equator. That contradicts our choice. That contradicts our placement of the points on the sphere. Let me make a small detour to tell you a personal story about the Borsuk-Ulam Theorem. Now, for many years, it was my dream to try and use the Borsuk-Ulam Theorem to actually prove something in a research paper. Okay, that was my dream. And at some point, I was working with my collaborator and good friend, Pavel Hrubish, on a problem that involved a family of sets. What we were trying to do is we were trying to find a small collection of subsets of 1 through n with the property that whenever you take any k elements from the universe, then you must have included most of the elements from one of the sets. Okay, the majority of the elements from one of the sets in the family that you pick. So we had a small collection of such sets in mind, and we were trying to prove that there's no better family of sets that had that property. And after thinking about this for a couple of days, I actually came up with a proof that our construction is optimal, and the proof used the Borsuk-Ulam theorem. So I'd finally achieved my dream, okay, which is my secret dream for a very long time. And I showed the proof to Pavel. I was very proud. And in a couple of hours, Pavel responded that actually you could just prove the same thing in 2 lines by appealing to the chromatic number of the Kneser graph. Okay, so I had to take my beautiful proof and throw it in the trash and just write 2 lines showing the reduction to the chromatic number of the Kneser graph. And I will never forgive him for doing that to me. Now, as I said before, there are many beautiful proofs of the Borsuk-Ulam theorem using different areas of mathematics. And here I want to show you a proof, my favorite one, that uses the concept of simplicial complexes. So let me start by introducing the concept of a simplicial complex. A simplicial complex is something that looks like this. Okay, it's a family of subsets of 1 through n. There's a bunch of vertices in the complex. Those are the ones that are numbered 1 through 13 in this picture. And then it consists of a collection of sets, each of which corresponds to a region of space. Okay, so here's an example of a 2-dimensional simplex in this complex, and it corresponds to the set 7, 3, 8. Okay, so these 3 points span this 2-dimensional simplex. Here's an example of a 1-dimensional simplex. It's the one spanned by these 2 points. And finally, this is an example of a 0-dimensional simplex. It's specified by a single vertex in the picture. Okay, so this is a simplicial complex. It's a collection of sets. And if you include, in this picture, if you include a 2-dimensional simplex, which is given by these 3 points, then every subset of these 3 points corresponds to another simplex that belongs to the simplicial complex. So that's a simplicial complex. Given such a simplicial complex, we will often work in the proof with the concept of a K-chain. A K-chain is a collection of K-dimensional simplices from the complex. Okay, so in this picture, these blue simplices together form a K-chain. And now you can identify the k chain with a binary string where you just specify, where every coordinate of the string corresponds to a k-dimensional simplex. Okay, there are n choose k plus 1, potentially such k-dimensional simplices. So you can make a vector where every coordinate corresponds to one of those simplices, and then the k chain corresponds to a binary string by specifying which of those simplices are included in the k chain. Okay, so that's a k chain. So this is an example of a 2 chain. This is an example of a 1 chain. This is an example of a 0 chain. Now, given a simplex in this simplicial complex, you can talk about its boundary. So here's an example of a simplex, and this is its boundary. The simplex is a 2-dimensional simplex. Its boundary is a 1 chain. It's a 1 chain. Okay, and in general, given any k chain, you can talk about the boundary of that k chain. So in this picture, the boundary of the k chain is this 1 chain. To compute the boundary of a k chain, just take the boundary of each k-dimensional simplex in the chain, which you can think of as a k-1 chain, and then take the corresponding vector of that k-1 chain and add up all of those k-1 chains modulo 2. Okay, so the boundary of the k chain C is exactly all of those k-1 simplexes that show up an odd number of times when you compute sum modulo 2. So in this picture, you see that 7, 3, for example, is on the boundary of both this simplex and this simplex. And so when you compute the sum modulo 2, you'll get 0. Okay. So 7, 3 does not belong to the boundary of this k chain, of this 2 chain. So that's the definition of the boundary of a chain. And it's easy to check that the boundary of any k chain is always 0. The reason you'll get 0 is that every k-2 chain that you get will show up twice in that process. Okay, and if the boundary of k-dimensional simplex is 0, then by linearity, the same must be true for every k chain C. Okay, so the boundary operator, you can think of it as a linear operator that maps k chains to k-1 chains. Next, we need the concept of a simplicial map. So say you're given 2 simplicial complexes, like in these pictures. So this is the first one, and this is the second one. A simplicial map from this complex to this one is a function that maps every vertex here to a vertex here. Okay, in such a way that a simplex is mapped to a simplex. So I want to assign for every vertex here a vertex here in such a way that a simplex will always be mapped to a simplex. So here's an example of such a map. So yeah, I've mapped this vertex to the vertex I, to this one to E, this one also to E. Okay. The map need not be injective. Okay, you can map multiple vertices to the same vertex on the right. But this map is a simplicial map because if you look at any simplex here, for example, this one, it's mapped to EF, which is a simplex on the right hand side. Okay, that's the simplicial map. Given a simplicial map H and a k-dimensional simplex sigma, let's write HK sigma to be equal to H of sigma if this is also a k-dimensional simplex, and 0 otherwise. Okay, so in this way, I've defined a map by linearity. I can extend this to a map that maps every k chain in the first simplex to a k chain in the second simplex, where I take, I map each of the simplices according to HK as I've defined here, and then I add up the resulting vectors modulo 2. Okay, so this is a map from the k chains of the first simplex to the k chains of the second simplex. Now here's a fact that will be crucial to us in the proof. It's not too hard to check that the boundary operator and these maps HK commute with each other in the following sense. The boundary of HK of CK is equal to HK minus 1 of the boundary of CK. That's a fact that will be very important to us. Because everything here is linear, in order to prove this fact, it's enough to check that it holds when CK itself is a single k-dimensional simplex. And that's not too hard to do. I'll leave it to you as an exercise. The interesting case is when HK of that simplex is 0. Okay, then you have to make sure that on the right hand side, all of the simplices that show up cancel each other. So armed with these concepts, let's now turn to trying to prove the Borsuk-Ulam theorem. So recall, this is what we want to prove. So we want to show that if you have a map from the n-dimensional sphere to n-dimensional space, then there's some pair of antipodal points that get the same value. Okay. Now the first thing I will do is I'm going to make a little bit of a transformation. So let's, for every vector v in n plus 1 dimensional space, let's define the L1 norm of the vector like this. This is the sum of the absolute values of the coordinate. And let's use this notation to denote the n plus 1 dimensional L1 ball, which is sometimes called the cross polytope. Okay, it's a set of vectors whose L1 norm is at most 1. And its boundary is the L1 sphere. It's the set of vectors whose L1 norm is exactly equal to 1. The first observation is that it's enough to prove the same fact for the L1 sphere. Okay, so I've replaced here the L2 sphere with the L1 sphere. Okay, but those two statements are equivalent, because if you have a continuous map for one, you can map it in a continuous way to a continuous map for the other. Okay, so from now on, I'm just going to prove this new theorem where the function is defined from the surface of the L1 sphere. Now suppose the theorem is not true. Then that means that there is a continuous function f such that for every x, f of x is not the same as f of minus x. Then we're eventually going to derive a contradiction. We'll start by first defining a continuous function g that maps the n-dimensional L1 ball to the n-1 dimensional sphere. And g is defined as follows. Okay, so g will evaluate f at x, and I have to create one more coordinate, and the last coordinate will be 1 minus the L1 norm of x. Okay. Minus f of minus x, and the last coordinate now will be minus 1 plus the L1 norm of x. And then we'll divide the entire expression at the top with its L1 norm. Now, because f of x is never equal to f of minus x, this is a well-defined function, right? The denominator here never vanishes. On the other hand, if f is continuous, g is also continuous. Okay, when you change x by a little bit, then the inputs to f also change by just a little bit. So the continuity of f implies that g is also continuous. Finally, g has a really nice feature, which is that it's antipodal on the boundary of the ball. Okay, so if you look at g on the value of the sphere, if x is a point on that boundary, then g of x is equal to minus of g of minus x. And that's because for x that's on this boundary, this last coordinate is 0. Okay, so when you evaluate g at minus x, that flips the signs in the numerator. Okay. So that's the kind of g we found. And now my goal is going to be to prove that such a g cannot exist. Okay, so now I'm going to start introducing a couple of simplicial complexes that will be helpful for us to reason about this and prove that such a g does not exist. So the first simplicial complex I'll use is just a very fine triangulation of the ball, of the n-dimensional L1 ball. So let's take a triangulation, meaning I'll partition the L1 ball into very small simplices, very small pieces, in such a way that whenever I have a simplex sigma in this triangulation, minus sigma will also be a simplex of the triangulation. Okay, so the triangulation is symmetric. And at the same time, the equators here, okay, the hyperplanes xi equals 0 for any xi, do not cut any of the simplices. So for example, in this picture, the equator xi, x1, x2 equals 0 corresponds to this line. And it just goes through the boundary of all the small simplices. It doesn't go through the interior of any of the small simplices. Okay, so I'll just pick a very fine triangulation that has these properties. That's my simplicial complex T. Okay, the simplicial complex consists of all of the small simplices I get in that in that triangulation and all the subsets, all the smaller simplices induced by those n-dimensional simplices. The second simplicial concept I'll need to use is the complex given by the faces of the L1 ball. Okay, so all of the sort of boundary faces of the L1 ball. So if EI denotes the ith basis vector in this space, the biggest simplices, the simplices of largest dimension in this simplicial complex are the n-1 dimensional simplices that correspond to subsets of plus or minus E1 through plus or minus En, which are of size n and contain for every EI exactly one of EI and minus EI. So those are the n-1 dimensional simplices of this simplicial complex. But in general, a simplex in this complex corresponds to a subset of these vectors with the feature that either only one of EI and minus EI can belong to the set. So if you have any subset S of these vectors with the feature that both of these do not simultaneously belong to S, then such a set S corresponds to a simplex in this simplicial complex. Okay. So these are two different simplicial complexes. Now we're going to use G to find a simplicial map from T to Q that's also antipodal on the boundary. So recall that we were given this function G, which is a continuous map from the ball to its boundary, in such a way that it's antipodal on the boundary. So what is the intuition here? Well, G is continuous, so if you pick the triangulation to be fine enough, okay, if you pick the basic simplices here that build up the triangulation to be very, very small, then you'll have the feature that nearby vertices in the triangulation get mapped to nearby points on the boundary. Okay, and we're going to use that fact to define a simplicial map from this simplex T to the simplex Q. And here's how that works. For every vertex in T, let K be the smallest coordinate such that the kth coordinate of G of Z is bigger than 1 over n. And if this coordinate is positive, we'll set H of Z to be Ek. Otherwise, we'll set it to be minus Ek. Now H is well defined because since G of Z has L1 norm exactly 1, there must be at least one coordinate of G of Z that has magnitude at least 1 over n. So that's the definition of H. And I claim that if this triangulation is fine enough, if the simplices are small enough in the triangulation, then H must be a simplicial map. And that's because if T is so fine that all of the nearby points A and B get G values that are within 2 over n of each other, then you see that it's not possible for those 2 points to get H values that are negations of each other. Okay, it's not possible that HA is equal to EK and HB is minus EK. Because if that was true, then the distance between GA and GB would be bigger than 2 over n. Okay. But that means that every simplex here gets mapped to a simplex here, right? It means that for every simplex here, it's not possible to get H values that are EK and minus EK on the vertices of the same simplex. So this gave us a simplicial map. And because G is antipodal on the boundary, H is also antipodal on the boundary. So now we're left with the following goal. We want to show that there is no simplicial map H that is also antipodal on the boundary. Okay. So in order to prove this, let's define a few objects. Let Vk plus 1 be the k plus 1 dimensional subspace that sets the coordinates k plus 2 on to be 0. Okay, so this is a k plus 1 dimensional subspace. And let's Ck be the k chain that contains all of the k dimensional simplices of T that lie in Vk plus 1 and also lie on the boundary of the ball. The key lemma, which is where all the work is happening, shows that if you look at hk of ck, that's equal to the boundary of a k plus 1 chain, which is antipodally symmetric. Okay. What does that mean? Antipodally symmetric means that whenever you have a simplex in the chain, then minus of that simplex is also in the chain. Okay. So this is the key lemma, that the image of ck is the boundary of an antipodally symmetric chain. The lemma leads to a contradiction, because if you apply the lemma with k equals 0, you see that it says this. Okay, H0 of C0 is the boundary of some antipodally symmetric one chain. But C0 consists of exactly 2 points, E1 and minus E1. And that means on the left-hand side, you have a set of size either 1 or 2. But I claim that the number of points on the right-hand side has to be a number that's divisible by 4. And that's a contradiction. Okay, so let me prove this claim first, and then we'll finally return to proving the technical lemma. So why does this claim hold? Well, suppose you're given some antipodally symmetric D1. I claim that the number of points on its boundary has to be divisible by 4. And here's why. So let's start at any vertex that lies on the boundary of D1 and follow the simplices of D1. They look like edges in a graph. Okay, and at the same time, start following the antipodal path. D1 is antipodally symmetric, so there's a corresponding antipodal path. And as you start walking along these paths, you have 2 antipodal paths that you're trying to generate. There are a number of things that can happen. The first thing that can happen is you might at some point find that the path wraps around on itself and you find a cycle. Okay. If that happens, you'll see the same thing happen on the antipodal side. And now you have 2 cycles that are antipodal to each other. Now you see, if you delete these cycles from D1, you obtain a smaller D1 that's still antipodally symmetric and has the same number, and it has exactly the same boundary as before. Okay, so in this case, we just delete those cycles and repeat the process. The second thing that can happen when you start exploring these paths is it could be that at some point, the first path hits the second path. First path hits the second path. In this case, you will find a single antipodal cycle. Okay, so a single cycle which is antipodal to itself. And again, you can just delete this cycle from the picture, and that doesn't change the elements of the boundary of D1. The third thing that can happen is that you can start at an element of the boundary and keep walking until you hit a point which does not have any other one simplices coming out of it, one-dimensional simplices coming out of it. Namely, you might hit a point that lies on the boundary of D1. But if this happens, it's also going to happen on the antipodal path. You end up with two antipodal paths that go from boundary points to boundary points, so you find in this picture 4 boundary points. And now if you delete these paths from the picture, you reduce the number of boundary points by 4, by exactly 4, and you can continue the process. So in this way, you will eventually eliminate all of the elements of D1 and count that the number of boundary points is a multiple of 4. So now let's return finally to the goal of proving this technical lemma. The proof is by induction. So the base case is when k is equal to n minus 1. So to prove the statement for k equals n minus 1, let an denote all of the n-dimensional simplices of the triangulation T. Okay. Then you see that hn minus 1 of cn minus 1, well, what is cn minus 1? It's all the n minus 1 dimensional simplices that lie on the boundary of T. All of the n minus 1 dimensional simplices that lie on the boundary. That's exactly equal to the boundary of a sub n. Okay, it's the boundary of a sub n. But the boundary operator and the h commute with each other, so I can switch that to write the boundary of hn of an. But you see, in Q there is no n-dimensional simplex. All the simplices of Q are of dimension n minus 1 or less. So hn of an must be 0. So I've expressed the left-hand side here as the boundary of 0. And 0 is an antipodally symmetric chain. Okay, so that proved the base case. To prove the inductive step, let's define C plus K to be the subchain of CK that consists of all of those simplices that lie above the equator xk plus 1 equals 0. Okay, so take all of the simplices where the coordinate xk plus 1 is greater than or equal to 0, and let's write C minus k to be the set of simplices in CK where the xk plus 1 coordinate is less than or equal to 0. Okay, so that partitions CK into 2 pieces, CK plus and CK minus. And because dk plus 1 is antipodally symmetric, we can write dk plus 1 as the sum of a plus b, where a and b are antipodal to each other, right? For every sigma that belongs to dk plus 1, minus sigma also belongs to dk plus 1. So take the pair sigma and minus sigma and split them into 2 parts and do this for every pair. That'll give you the chains a and b, okay, which are antipodal to each other. And now you see that I can write hk of ck plus hk of ck minus as hk of ck. Okay, because ck is the sum of these 2 chains. Okay, but by induction, we have that this statement, this thing is equal to the boundary of dk plus 1, which is the boundary of a plus the boundary of b. Okay, so that's the inductive hypothesis applied for k. If I rearrange this, what I get is this equation. So I've just rearranged the equation up here. But now you see something very interesting has happened, because in this equation you see that the left-hand side is antipodal to the right-hand side. Right? If sigma belongs to the left-hand side, then minus sigma must belong to the right-hand side. By the choice of ck plus, c minus k, ck minus, and also a and b. But then you see it must be that the left-hand side itself is antipodally symmetric. Okay, if sigma belongs to the left-hand side, minus sigma also has to belong to the left-hand side. Okay, So define dk to be the left-hand side here. It's antipodally symmetric. And now if you take the boundary of dk, okay, that's the boundary of the left-hand side here, what you see is the first term, again using the fact that the boundary operator commutes with h, is equal to this quantity. And the second term here is 0 because it's the boundary of something. Okay, so what you're left with is this quantity, but the boundary of ck plus is exactly ck minus. So that completes the induction. We started with the assumption that it holds for k, and we arrived at the same statement for k minus 1. Okay, so it's a beautiful proof involving many nice ideas. I hope you enjoyed it. There are many nice references for Borsuk-Ulam Theorem, but most of the ideas that I've discussed in this video can be found in some notes that I'll link to in the description of the video. I hope you enjoyed it.